Make sure to turn on the projector this time. So, yeah. So, the interesting thing about, I mean, the HCS final that you're not taking for this class is that there are no calculators allowed. At all.
Oh, is there math? That means they can't make us do terribly hard math.
No, they don't make you do terribly hard math. Instead, what they do is like, what it would be is, right, so I guess you can see the screen, right? Something like this, where like, what is the entropy for some process, right? And one of the answers would be like this. It would be the numbers plugged in for the variables, but not actually, you know, simplified down to 7.24 joules per Kelvin, right? So you'd have different things like this, or you'd have like this formula, or maybe this with these two numbers swapped, or, you know, maybe a formula with like P delta V or something, you know, like, yeah. Yeah. So, but yeah. But obviously, that's not the final you'll be taking, so. All right. Welcome everyone. Welcome those here on Zoom. All right, so I was going to check. Anyone happen to have a copy of the homework with them? So I don't have to try to pull it up. No, all right, that's fine. I'll pull it up. It's on my phone real quick. The convenient Canvas app.
Do you like using tracks or Canvas more?
I mean, I've learned more about how to use Canvas versus how to use tracks. So I guess I'll say Canvas because, you know, I used tracks for like, you know, I guess a year and a half or so before using Canvas or something, 2 years, I guess. And when I used tracks, it was basically for files. I basically put files on tracks and put grades up on tracks, and that was it. You know, here I'm doing a lot more with Canvas, so I don't know. There are some things that are more annoying about Canvas. Like every document that is uploaded, you have to tell Canvas that you have copyright permission to have that document available online before it can be viewed. So it's like an extra step with uploading files. It's kind of annoying. You can't like default say, yes, I have the copyrights. You have to manually do for each file. All right, homework, what's this, homework 3? Yep. I know there's some delta G questions on here, so I just want to take a look here. I think we'll cover what needs to be covered for this. I think so. I was just reminding myself what delta G questions are on here. And it's just like 2 that are related with delta G. So I think we'll be fine. We'll see at the end of the class. I'll, you know, make an announcement, say whatever about the homework as to whether or not we'll drop a question, extend it a day or something like that. And by a day, I mean extend it to the next class day, not like extend it to Saturday or something, right? So yes, I have more examples here of kind of stuff we've done, talked about last time. So yeah, let's do that. Let's start off with doing some of these examples. We'll kind of just talk them over together, not necessarily take a lot of time working them out on your own and then working them together, but just kind of talk them over together, right? So in this example, right, I have 0.35 moles of an ideal gas, or we're given the molar heat capacity at constant volume. And this ideal gas is expanded isothermally at 295 Kelvin against a constant external pressure of 0.81 atmospheres from 0.35 liters to 4.21 liters. Question is what is delta S of the surroundings, and delta S of the universe? Okay. So how would I get delta S of the inverse? It's a very simple one. Yeah, right? Delta S system plus delta S surrounding, right? That's right. So delta S universe, you just add the first two delta S's together to get that simple, right? How do I find the entropy change in the surroundings? Yeah, in this case, you'd want to use Q, right? So that minus delta H is specifically for constant pressure, mechanical equilibrium cases and things like that, whether it be a chemical reaction or some other type of like heating of a balloon, right? Yeah, otherwise you use Q, right? So minus Q over the temperature of the surroundings, which is 295 Kelvin, right? In this problem, everything's at a constant temperature of 295 Kelvin, right? So temperature of the system, temperature of the surroundings are all 295 Kelvin, right? So in an isothermal problem, typically it's not going to state that 295 Kelvin is the surroundings temperature, right? But if that's what the temperature of the system is and it's being held constant, temperature of surroundings is going to be the same thing, right? If you have a problem where temperature in your system is changing, it will typically state what the temperature is of the surroundings if you need to know, right? So anyway, so right, temperature surroundings 295 Kelvin, right? And so how do we get the Q of the system, right? The heat transfer in the system. What's that going to be related with for an isothermal process? So most times delta H. So that will be true if we had some sort of a chemical reaction going on or a phase change. But in this case, we're just doing an isothermal expansion, right? So for an isothermal expansion or compression of a gas, right, where number of moles are being held constant, right, what is delta U equal to? Let me open up the chat here in case people are saying something. Yeah, delta U will be 0 for this process because it's an isothermal process where the number of moles are staying constant. Okay, right? And so delta U as well as delta H are 0 for this process, which if delta U is 0, what does that tell you about the relationship between work and heat? Right, they're equal and opposite signs, right? And so Q is just minus W. And then how would I get work for a constant external pressure expansion? Right, yeah, so minus P external delta V. So for the surroundings, right, because we know the process is done isothermally, we know Q is minus W, and we know work is minus P external delta V. Q is just positive P external delta V. And then delta S of the surroundings is the minus Q of your system, right? Reversible, irreversible heat, whatever it is, right? Just the Q for the process you did, divided by the temperature of the surroundings, which is minus P external delta V, right? P external was 0.81 atmospheres. There's our change in volume. I need to convert that to joules, right? So that 101.325 is that conversion to joules, divided by the temperature of the surroundings, okay, which is 295 Kelvin. And you get this minus 1.07 joules per Kelvin for the delta S of the surroundings. Okay. How do I get the entropy change for the system for an isothermal expansion of a gas? Yep. Right, so a number of people are starting to say that's right. NR ln V final over V initial, right? For isothermal expansion of a gas, right? Now, while the actual step was done irreversibly, right? I can imagine doing the exact same change in state, but instead of expanding against a constant external pressure, I expand against a changing external pressure, where the external pressure is equal to the pressure of my gas, and that makes the expansion then a reversible expansion. Okay, when I do that. And so, right, and so along that reversible pathway, right, the entropy change I can calculate is just minus NR ln V final over V initial, which is the same entropy change for the irreversible isothermal expansion, okay, which you just plug in for N. R here, we're going to use the joules per Kelvin mole version, so 8.314, and then natural log of your final volume over your initial volume, and that gives you a final entropy change of a positive 7.24 joules per Kelvin for your gas. Yes. Go back to the surrounding entropy.
Yeah.
We just wanted to see the work, or is there kind of a question you?
I was just like confused for delta S, not the surroundings. Why can't you just do it as Q reversible of the system? Oh, okay, never mind. I think I see.
Yeah, right. I mean, so we can't do like Q of the system divided by T of the system, right? Because in this case, the Q is irreversible heat transfer, not reversible. So we need to calculate the reversible heat transfer from the same initial and final states, right?
But
Which,
you don't need to calculate it reversibly for the surroundings.
no. For the surroundings, you don't. For the surroundings, it's not dependent upon the reversible heat transfer. And this has to do with, again, to the fact that the surroundings, that the reversible and irreversible heat transfer in the surroundings will end up being the same. Because the surroundings is a constant temperature, pressure, volume system, so the heat transfer in the surroundings is equal to the internal energy change or the entropy change of the surroundings, which is independent upon how it was done. And so the reversible and irreversible heat transfer in the surroundings is the same. And so you can just use the irreversible heat for this. And so you can always do that for the surroundings. For the surroundings, you always use the heat transfer in the actual problem that's given. For the entropy change in the system, we have to create a reversible path that connects the same initial and final states. Which again, in this process, the reversible path is like, just a single path isothermal reversible instead of an isothermal irreversible expansion. Right. And that gives us, again, an entropy change of 7.24 joules per Kelvin. Right. All right, and so the entropy change of the universe is just entropy change of the system plus surroundings, which is a positive 6.17 joules per Kelvin, right? By adding up that 7.2 minus 1.07. Which this process is then spontaneous, right? Because the entropy change of the universe is greater than 0. So questions about this problem? Right. Again, we should get ourselves comfortable with answering questions like this. Okay. You have plenty of practice on doing this on the homework. Okay. And again, I think it's at some point, when I have some free time, I'll try to sit down. Sorry, my normal daily setting to turn itself off. Okay. So this is the exact same problem, but now the external pressure is 20 atmospheres. instead of 0.81 atmospheres. Right? I assume there's audio now, correct? Yeah, okay, fantastic, thanks. Yeah, sorry, I promise you I am doing nothing. The microphone in this room just decides to like randomly stop working, and I just have to like click a button to get it to work again. So, yeah, all right, so for this process, right, how do I get the entropy change in the system? Right, the exact same way, right? NR, ln, V final over V initial, right? The same, just isothermal expansion of a gas. Doesn't matter how it was done, okay? Right, the entropy change in the system is going to be identical. Okay. Now, we need to calculate about the entropy change in the surroundings. Okay. And so how do I get the entropy change in the surroundings? Right, yeah, minus P external delta V. Okay. Right now, the external pressure is 20 atmospheres. Okay. So plug that in. And entropy change in the surroundings is now minus 26.5 joules per Kelvin. Okay. So the entropy change in the universe is now that positive 7.24 joules per Kelvin minus 26.5 joules per Kelvin, right? Which gives us a total negative 19.26 joules per Kelvin. Okay, this is not a spontaneous expansion, right? Right, and the reason is because if you calculate using the ideal gas law the pressures of your gas initially and finally, right, the final pressure of the gas is 2 atmospheres, okay? So while the initial pressure of your gas, 24, is greater than the external pressure of 20, at some point you start expanding your gas against an external pressure that's greater than the pressure of the gas, which is not going to happen spontaneously, right? It's only going to happen if I like help push this piston, if you will, to expand to its final volume, right? If I use some outside intervention to help expand the gas's volume to the final point, right, the gas itself isn't going to naturally expand itself to a final volume of, what did I put, 4.21 liters, right, if the external pressure is 20 atmospheres, because it just, right, is going to reach a point where the internal pressure reaches 20 atmospheres and it's going to stop expanding because it's not going to have the force to expand past that, right? And so if I want to get this full expansion, I have to do outside interventions to my system, right? I got to pull on that piston or something like that, right, in order to get it to expand freely and naturally to that final volume, right? Well, in the first problem, the final external pressure was 0.8 something atmospheres, which is still less than the final internal pressure of your gas of 2 atmospheres. Okay? And so that your gas will freely expand spontaneously against that external pressure because it's got more force, the external pressure, okay, and to do that, right? So question here, can we assume the problem is isothermal only when we're given process is occurring on one certain temperature? So you should never assume a problem is isothermal. It should tell you the problem is isothermal. Okay? So sometimes you might be told only one temperature, but it might be done, say, adiabatically, and you got to calculate that final temperature. It might be done at a constant pressure or a constant volume, and you got to use the ideal gas law to calculate that final temperature. So just because you're potentially given one temperature doesn't necessarily mean the process is isothermal. Okay, so the problem itself will tell you whether or not it's isothermal explicitly. Okay, to know that, right? All right. Questions about this? Right. And so, as sort of a note right here, right, even though my change in my system is the exact same for the 2 questions here, right, the change in the surroundings is not. Okay, and that's why delta S of surroundings is different. For one, my surroundings is different between the two problems, right? In one problem, my surroundings has a pressure of 0.8 atmospheres. In this problem, surroundings has a pressure of 20 atmospheres, right? So already you can see the surroundings is different. So the entropy change should be different for the surroundings, okay? Right? And so, yeah. And it's the same thing for if I were to expand my gas, let's say here. I lost my train of thought, but yeah. So anyway, so that's why the entropy change in the surroundings is different between the two problems, right? It's because the surroundings itself is different, right, between the two problems. So that's why its entropy change is different. Okay? All right. So other questions about those examples? All right, so the third law of thermodynamics is a pretty simple one. Just states that the entropy of a perfect crystal, right, with no defects or anything else like that, at 0 Kelvin is of an element, right, or compound, right, that is in a perfect crystalline form, is just equal to 0. Okay, that's the third law of thermodynamics. It's just saying, you know what, there is a 0 entropy, and it is a substance at 0 Kelvin that is a perfect crystal with no defects. Okay, and that's what 0 entropy is. Okay, right. And so one of the implications of this is the fact that that entropy, right, is an absolute quantity, just like internal energy, right? Right, an object has some internal energy that's related with its total kinetic energy and its total potential energy, right? Every substance has some entropy, okay, right? And so every element, right, has an entropy, right? Which again is different from enthalpy, where there's no absolute values, right? And so we always talk about enthalpy of formations, which are always relative to things, right? Enthalpies are always relative between this and that, right? What's the difference in enthalpy between this thing and that thing, right? Right. Enthalpy of formation is what is the enthalpy change when I go from an element to some molecule, right? Okay, and so, but entropy, just like internal energy, has absolute quantities, right? A substance has some entropy, has some internal energy. Okay. Right? And so if I wanted to get the entropy of some substance, right, I could imagine heating, say, the solid, right, from 0 Kelvin to its melting point, then melting the solid to a liquid, heating that liquid to its boiling point, vaporizing the liquid, and then heating the gas from its boiling point to whatever final temperature it is, right, for my gas to get the total entropy of my gas, right? Because I can calculate the change in entropy of all these substances, okay, right? But the initial entropy is equal to 0, so the final entropy is just equal to that change in entropy, right? So the final entropy of my gas S would just equal the change in entropy from the 0 Kelvin entropy to the entropy at that final temperature, okay? Right? Now, if I were calculating the entropy of just, say, a solid, I would just heat the solid from 0 Kelvin to whatever temperature it is of the solid, right? And this change in entropy would give me the entropy of that solid, right? So you know, depending on the final phase, depends on whether or not you need to go through steps 1, 2, 3, 4, and 5, right? Okay. Now, note, right, for all of these things, we assume, right, all these equations for steps 1, 3, and 5 assume a constant heat capacity, which is not true, especially for solids at low temperatures. Okay. At low temperatures, the heat capacity for a solid depends on the temperature cubed, okay, which is not a constant. But, and so basically, based off of this, if I want to get the entropy change for a reaction, right, it's just like the kind of enthalpy change that we talked about in chapter 2 of the book, right, where it's the entropy of your products minus the entropy of your reactants at their standard states. Okay, So the little circle here on the top is indicating standard states, right? Which, if we recall, is, you know, whatever phase it's at the temperature you have, right? With 1 bar pressures, 1 molar concentrations, depending on if you have an aqueous or a gas species, okay? Right? But the entropy change for a reaction is just the entropy of the products minus the entropy of the reactants multiplied by their stoichiometric coefficients, okay? Right? And again, note that these are entropies, not entropy of formations, okay? Right? So entropy, so O2, for example, right, has entropy, right? Again, O2 gas has an entropy. It does not have an enthalpy of formation, but it does have the standard entropy, okay? Right? So there are standard entropies that are not 0 for pure elements in the standard states, right? The only time the standard entropy of a pure element in its standard state is equal to 0 is when it's a crystallized element, right? Otherwise, entropys are going to be non-zero for everything, okay? Which will never do a problem relating with something having 0 entropy, right? So don't need to worry about that, right? So questions about this third law of thermodynamics and its implications, right? So the third law of thermodynamics is just stating essentially what is the 0 entropy, you know, perfect crystal, 0 Kelvin. And then based off of that, we can, you know, calculate what standard entropy is for any substance at any temperature, okay? And we can get the entropy changes for reactions based off of the standard entropies of your reactants and products. All right. So if ice melts at 273 Kelvin, right, and the liquid water boils at 373 Kelvin, right, which of the following would I need to know to calculate the absolute entropy of water at 350 Kelvin? Do I need to know the CP from low temperatures to 273 Kelvin? Do I need to know the CP from 273 to 373 Kelvin? Do I need to know the CP above 373 Kelvin? Do I need to know the entropy of fusion? Do I need to know the entropy of vaporization? Anyone have any? D, is that what I heard? Oh, B. B is in boy, bravo. All right. Right. So, right, if I want to know the absolute entropy at 350 Kelvin, right? Well, 350 Kelvin is lower than the vaporization temperature of water, right? So I shouldn't need to know what the vaporization temperature is, and I shouldn't need to know what the heat capacity is above 373 Kelvin, right? But I will need to know, right, heat capacity from 0 Kelvin to 273, and the heat capacity from 273 to 373. And then I will need to know the entropy of fusion, right? And so I need to know 1, 2, and 4, so B here. All right. So what the question here is, what is the molar entropy change for the formation of N2O5 at 298 Kelvin, given the standard molar entropies of N2O5, N2, and O2? All right, anyone have any
None of the above.
some E's here? All right. E is correct. So some people potentially could have gotten C minus 653.5 joules per Kelvin. And the reason why that is not correct is, so, right, this problem talks about the formation reaction of N2O5. Let me swap over here. Right, the formation reaction of N2O5 is N2 plus 5 halves O2 forming N2O5 with the stoichiometric coefficient here of 1, right? If you did 2N2 plus 5O2 going to 2N2O5, you will get the answer C. But it should be the answer C divided by 2, right, which is not there. And so it is, in fact, E, none of the above. Okay. You do that, right? And you get that, again, by taking 377.7 minus 191.61 minus 5 halves times 205.138. And that will give you, what's that number? Again, divided by 2. Say that again? Yeah, negative 376.8, you know, roughly rounding, right? Okay. Which none of these are negative 326, right? Or 327. Okay. So none of these are correct. And so E is going to be the right answer. Okay. Questions?
These not close enough to 28 off.
I mean, with like the like, you'd have to do some weird rounding to get to like 334. So. Yeah. All right. All right. So in this problem, Danielle, answer on your that question was E. So it was E. You're not able to hear me. I typed it in chat. E, none of the above. Okay. All right. All right, so in this problem, right, we're wanting the entropy change from 300 to 400 Kelvin, right, which what's going on is we want, right, at 300 Kelvin, shoot, I forgot to write down, was it given a moles, a volume, or is it just, I need to get the molar entropy change, I forget the problem, you don't remember? I might just need the molar entropy change if function based on this data calculate 1 mole. Okay, 1 mole. Right. Number of moles is 1. That's n equals 1. Right. So number of moles, right, is equal to 1. Okay. Right. So I want 1 mole at 300 Kelvin of H2O liquid to, right, 1 mole H2O gas at 400 Kelvin. Okay. Right, so that's at 300 Kelvin, 1 mole of liquid, so 1 mole of gas at 400 Kelvin, right? To get there, right, I'm going to have to, oh my goodness, I forgot, I froze the screen. Right. Sorry. Thank you for that. Sorry. Right? So I just wrote down the information given the problem, right? So to get this change of 300 Kelvin to 400 Kelvin of liquid to gas, right? First, I got to heat up my liquid to 373.15 Kelvin, H2O liquid, right? I then change that to 373.15 Kelvin H2O gas, and I heat my gas up, right? So I have delta S1, delta S2, delta S3. Okay? And I'm going to assume, right, that given the CPs are given this problem, right, I'm going to do this as a constant pressure, reversible process, right? So I can calculate the entropys for steps 1 and 3 here. Okay. Right, so my total entropy is just the sum of these entropy changes, right? Delta S1 is a constant heating of a liquid, right? It's going to be 1 mole times its molar heat capacity, which is 33.6 joules per Kelvin mole, times the natural log of final temperature, 373.15, divided by the initial temperature, 300. Okay. Right. Delta S3, I'm just going to do that right now because it's very similar, right? Now it's the molar heat capacity of the gas, joules per Kelvin mole. The natural log of the final temperature of 400 Kelvin over 373.15. Okay. And then delta S2, right, is just the enthalpy change of vaporization times 1 divided by the temperature of vaporization, which is 373.15 Kelvin. Okay. Right?
Quick
Yeah.
question.
Uh-huh.
Why did you use CP gas and S1?
Oh, sorry, because I misread my own labels. That's 3 and 1. It's because, crap. Yeah. Yeah, sorry. Yeah. 1, 3. So we get for doing things in pen, right? So thank you. There we go. Sorry, I used the wrong CPs. For those who potentially didn't hear the comment from the students, right? The heat capacity I used for the liquid was the gas one, and the gas I used for the liquid. So I used the wrong CPs with the temperature. So yeah, so 75.3 is the heat capacity for the liquid, okay, and that is corresponding with the change in temperature of the liquid from 300 to 373.15 Kelvin, right? And so yeah. So that is how we calculate the entropy change for this entire process. Right, so step one, right, 1 times 75, that heat capacity of the liquid, times the logarithm of the temperature change gives us 16.83 joules per Kelvin. Next, for step 2, I just take the enthalpy of vaporization times 1. Now I convert this to joules, right? Enthalpy of vaporization was given kilojoules. I'm going to convert this to joules. Divided by the temperature of vaporization, which is 109. It gives me 109 joules per Kelvin. And then finally, for step 3, I use the heat capacity of my gas times the number of moles of 1, and then 400 divided by 273, which gives us 2.16 joules per Kelvin. So I add these three things together to get a final value of 128 joules per Kelvin for the entropy change for taking your liquid at 300 Kelvin to a gas at 400 Kelvin. Any questions? Yeah. So you could have your final answer in kilojoules per Kelvin if you wanted to. Yeah. And convert the other answers to kilojoules, and that's fine. Whichever way you prefer, that's fine. Just you have to make sure you're consistent, right? When you're adding the entropys together, that they're all in joules or all in kilojoules. That's all, right? But either one is fine. Mm-hmm. Any other questions? All right. So let's talk about Helmholtz and Gibbs free energy. Okay. So in some of the problems we talked about at the beginning of the class, we measured the entropy change in the universe in order to determine the spontaneity of the problem. Okay. Right. And that's again because of our second law of thermodynamics, which tells us, right, that the spontaneity of a problem is given by the entropy change in the universe. Right. If something is to be spontaneous, that means that change in entropy of the universe has to be greater than 0. Okay. So second law of thermodynamics is always going to be true. Okay. But we don't want to measure the entropy change in the universe, right? Because in order to get the entropy first, I got to get the entropy change in the surroundings. And if you're in lab, right, it can potentially be annoying to try to measure, calculate, figure out what the entropy change in your surroundings is. Okay? And so we don't want to have to necessarily do that, right? Because right in lab, we care about our system, right? We take very delicate care to make sure our system is at certain temperatures, certain pressures, certain volumes, certain things are being mixed together, right? We do a lot of care for our system, right? We don't so much, okay? Right? We measure things in our system. We have lasers pointed at our system, measuring things, right? And all sorts of stuff, right? So we care about our system. We do not care as much about the surroundings, right? And so ideally, we like to measure spontaneity by just measuring changes in the system, okay? And this is where we get our Helmholtz and Gibbs free energy from, okay? So if you define Helmholtz free energy, so A here is the Helmholtz energy. If you define that as the internal energy minus temperature times entropy, and if you then look at some change in state that's done under constant temperature and constant volume conditions, then when the change in Helmholtz free energy is less than 0, that implies the process will be spontaneous, okay? And that's because an entropy and Helmholtz free energy change less than 0 at constant temperature volume conditions is the same thing as an entropy change in the universe being greater than 0. Basically, under constant temperature pressure conditions, the Helmholtz free energy is equal to the entropy of the universe, okay? Essentially. Or more, the change in entropy of the universe is related with the change in Helmholtz free energy, okay? Right? With a minus sign. So negative, right? So, let's see here. I'll just write it out, right? At constant temperature and volume, delta A minus delta A, delta S universe. Okay. Right. And so a positive entropy change in the universe is a negative Helmholtz free energy change in your system. Okay. And again, this is only true. This equality is only true if you're under constant temperature and volume conditions for your system. If you are not under constant temperature volume conditions for your system, this is not true, and the Helmholtz free energy tells you nothing about spontaneity. Okay. Right. Now proving that relationship is done in the videos online. You can always check that out. Okay. But basically, you kind of start from definition of entropy change in the system and the surroundings, use some manipulations of those things, assuming constant volume conditions, to get to this final relationship. Okay? Basically, what you get is that under constant temperature conditions, right, the entropy of the universe is related with the internal energy change of the system minus the temperature times the entropy change of the system. Okay? And so we just define that as the Helmholtz free energy. Okay? And again, so the Helmholtz free energy, right? This Helmholtz energy is what it's defined as, and I could always measure this for any change of state I want, right? And that's fine, and it has some value for every change of state, right, that I ever do. But its meaning, in terms of it's telling us about spontaneity, only occurs under constant temperature volume conditions. If I do some process under constant volume conditions, but the temperature is changing, Helmholtz free energy will not tell us anything about whether or not that process is spontaneous. Okay, all right. But again, I can measure the Helmholtz free energy change for my process under any conditions. It's only under constant temperature volume conditions is it spontaneous. Okay. So, right. Right, and on constant temperature, we can get the change in Helmholtz free energy by measuring the change in internal energy and the change in entropy of our system, right, using this formula. Okay. Similarly, we get free energy by looking at constant temperature and pressure conditions, right? And again, this is why in lab we care about enthalpy and why we care about Gibbs free energy, because in lab we're under constant temperature pressure conditions typically, right? And so right, under constant temperature pressure conditions, a negative free energy change tells us about spontaneity. But again, it's only under constant temperature pressure conditions, right? Which is again why for chemical reactions, we look at free energy change. Because for chemical reactions, we're almost always doing those under constant temperature pressure conditions. So the free energy change of a chemical reaction will tell us about the spontaneity of that chemical reaction. Okay? But the free energy change for the adiabatic expansion of a gas tells us nothing about its spontaneity. I can measure the free energy change, but that doesn't tell me whether or not it's spontaneous. Okay? Because for a adiabatic expansion of a gas, its temperature and pressure will change, and so it has no relationship with spontaneity. Because it's only under constant temperature pressure conditions does the negative free energy change equal the entropy change of the universe. Okay? So again, that relationship between Helmholtz free energy and entropy of the universe holds true only under constant temperature volume conditions, and the relationship between Gibbs free energy and entropy change of the universe only holds true under constant temperature and pressure conditions. Okay? All right. So this is how we get the entropy change, right? Or the Gibbs free energy change under constant temperature conditions by getting the enthalpy change under constant temperature conditions, right? And then subtracting off the temperature times the entropy change under those constant temperature conditions. Okay. Right? So kind of talking more about Gibbs free energy, right? So I can look at then whether or not something will be spontaneous under low or high temperatures or always or never by looking at the enthalpy and entropy changes, right, for your process, right? And so, for example, right, basically, if I want my thing to be spontaneous, delta G has to be less than 0. Well, looking at this equation, delta G is always less than 0 if delta H is negative and delta S is positive, right? So that's what this table is saying, right? If delta S is positive, delta H is negative, right? Then delta G is always less than 0. So any temperature of this process is always spontaneous, right? And then, you know, you have things like only at high temperatures is something that's endothermic with a positive entropy change spontaneous, right? And that's only spontaneous at high temperatures, right? Because then it's being dominated by the entropy, which, right? Entropy always wants to increase for a spontaneous process. Enthalpy wants to decrease for a spontaneous process, right? So in order to have an increase in enthalpy, you have to have a much greater increase in entropy, right? And again, looking at this equation, right, you're multiplying your entropy by temperature. So at very high temperatures, the entropy change is going to be magnified even more, and it's going to dominate the enthalpy change, and you're going to have a spontaneous process. Okay? Similarly, if you have a negative entropy change, this is only, and something that's exothermic, that's only spontaneous at low temperatures, when the entropy times the temperature is negligible compared to the enthalpy change. Okay? So again, this table here is just being filled in by looking at this equation up above and saying, okay, under what conditions is delta G negative, right? Questions about this? And hopefully you've seen something similar to this when talking about Gibbs free energy and Gen Chem and things like that. At least I know I talk about it in general chemistry, but potentially not everyone does. All right. So actually, I think we already did a problem like this. I want to go my next set of slides here to what's that? Talking more about Helmholtz, Gibbs free energy. Okay. Let's do some questions related with that. Okay. So for a certain isothermal and isobaric process, delta H is equal to 96 kilojoules. That is positive 243 kilojoules. It's spontaneous at room temperature. Okay. So a lot of people are just outright saying no. Okay. So isobaric, right, is constant pressure. Just so you remember, so constant temperature, pressure conditions, right? So in order to determine if this is spontaneous, we need to calculate the free energy change. Okay, it's going to be delta H minus T delta S. To do that, you want to calculate this, right? You want to calculate delta G. So you're going to be 46,000, right? Convert that to joules, minus 298 times 243. So we calculate that, 298 times 243. It's going to be minus 72,414. And so taking that difference, this delta G is going to be minus 200, or I'll convert this back to kilojoules, minus 26.4 kilojoules. So you could have converted this to 0.243 kilojoules per Kelvin and done everything in kilojoules or whatever, right? What?
I thought it was 96 kilojoules.
Oh, shoot. That is a 9. So that'd be a positive. So it is positive. So delta G is greater than 0 because it is 96. Thank you. Sorry. Couldn't even read my own handwriting. How sad. All right, so yeah, positive 96. So yeah, so this will be spontaneous at room temperature. or it will not be spontaneous. Sorry, it's not spontaneous at room temperature because delta G is greater than 0. So the next question posed to you is, at what temperature does it become spontaneous? Since we already determined it's not spontaneous at room temperature, what temperature must I be at for this process to become spontaneous? Right. So, right, if I want to figure out when does this become spontaneous, right? Well, my free energy, right, is a measure of my spontaneity, right? Free energy, delta G equals delta H minus T delta S, right? Well, assuming delta H and delta S are constant with temperature, right, this is just an equation for a straight line, okay? Right? So if I have delta G as a y-axis, temperature is x-axis, right? I'm going to have some straight line, right, with a negative slope. So it's going to go, something like this, right? So it's going to have some region where it's greater than 0, and then some region where delta G is less than 0, right? Well, when I transition from greater than 0 to less than 0, I'm at some point, right, where delta G equals 0, right? So when the free energy change equals 0, right, that is the point which it's going to transition between spontaneous and non-spontaneous, right? This is the point where you're at equilibrium, right? This is, right, for constant temperature pressure conditions, right, this is an equilibrium, right, condition, state, right, reversible process, right, because this delta G is related with minus delta S universe, right, and when the universe entropy change is equal to 0, right, that's a reversible process, a process at equilibrium, okay, right, and so, right, when you're greater than this delta G equals 0, right, that's when you're non-spontaneous. And when you just become a little bit below this, right, that's when you become spontaneous. So we want to solve when delta G equals 0, right? So I want to know when 96 kilojoules minus T times 0.243 kilojoules per Kelvin is equal to 0. So to do that, you just get T equals 96 divided by 0.243, which equals 350, 395 Kelvin. So 395, any temperature like equal or greater than 395 Kelvin, I mean technically not necessarily equal, but any temperature greater than 395 Kelvin, this process is now spontaneous. Okay. Yeah.
So when delta G is greater than 0, it's non-spontaneous, and when it's
Yep.
less than 0, it's spontaneous.
Yep. Yeah, it's opposite of the entropy change of the universe. Yeah. And I guess whoever, Gibbs, when he first came up with this, decided he wanted delta H minus T delta S instead of T delta S minus delta H. Because if you did T delta S minus delta H, then it would be delta G greater than 0 spontaneous, delta G less than 0 non-spontaneous. But, whatever choice is, decided one something like this. Maybe because he's thinking of it as an energy, and typically our energies are negative, our internal energies are negative values, and things like that. But it's slightly arbitrary, right? So how you define, right, Gibbs free energy as H minus TS. You could have defined it as TS minus H, right? But it was defined as H minus TS. So negative delta G is spontaneous, and a positive delta G is non-spontaneous. Other questions about this problem? Right, and this is just kind of a reminder, right? So this is an example of something that's only spontaneous at lower temperatures, right? Going from a gas to a liquid only happens at low temperatures, right? Below your vaporization temperature. Okay, but again, the thermodynamic stuff applies to everything, not just our chemical reactions. Okay, but again, when we talk about spontaneity, we don't necessarily mean rapid, right? Spontaneous and the time it takes to achieve that process are independent of each other. Okay. So, let's see. I'm kind of doing some of these. I was hoping I had. Nope. Thought I had. Yeah. Yes. All right. So let's talk. We'll jump ahead and talk about this because this is fairly straightforward, right? If I have the change in free energy, right, is equal to change in enthalpy minus T delta S, right? So the change in free energy, Gibbs free energy of a reaction is just the enthalpy change of that reaction minus temperature times the entropy change of that reaction, right? Which we've seen and used before in chemistry, right? And then you potentially see this equation, right, which is then the Gibbs free energy change for a reaction is also related to the Gibbs free energy of formation of your products minus reactants, which again is the same exact equation as the enthalpy change for a reaction, okay? Just replace H with G, and you got the exact same equation, right? Okay. Notice that standard formation Gibbs energies are also defined as 0, just like enthalpy, right? Gibbs free energy is not an absolute value, an absolute quantity. So we define Gibbs free energies as standard Gibbs free energies of formation of species, like we do for enthalpies. Okay. So delta G of formation of O2 gas is 0. Okay. Because it's talking about the free energy change for that formation reaction, which the formation reaction of O2 gas is no reaction. Just O2 gas going to O2 gas. Okay. Right. So given the Gibbs free energy change of formations for these different species here, right, what is the standard molar Gibbs energy change for the reaction? Right, so below each compound is written energy of formation, Gibbs free energy of formation, right? O2 is 0, CO is minus 173, CO2 is minus 290 or minus 394. Right. So how would I get the free energy change for this reaction? Right, yeah. So I do products minus reactants, which is negative 394 minus a negative 173.17, which ends up being a plus 173.17, right? So just do, oh, I did not have the answer written down right, but whatever 394, what is that? Yeah, so negative 257 kilojoules per mole, right, would be the Gibbs free energy change for this reaction, okay? Right. So we do this the same way we do enthalpies, right, of formations and things like that. Okay. See if I have another example of this. Nope. Let's see here. Question 03, it's entropy change. Reaction is negative molecular capacity. Is it 200 Kelvin, assuming delta H and delta S are constant. Okay. So, yep. All right. So again, the enthalpy of formation reaction of O3, okay, at 298 Kelvin, as well as at 200 Kelvin. And in the first part, we're going to assume that enthalpy and entropy are constant. In the second part, we're going to assume that the enthalpy is not constant. Actually, technically, we could assume entropy is not constant as entropy changes, but we won't do that in this class, but you could. For sake of time, we'll just kind of talk about this problem, right? So the first thing we need to do for this problem, right, is we have a chemical reaction we're interested in, right? The enthalpy of formation reaction of both. So the first thing we want to do is write out what that reaction is. Of course, I don't have it written out. Oh, it is stuck in here. 3/2 O2 going to O3. That is the enthalpy of formation reaction, or sorry, the formation reaction of O3, right? The formation reaction of O3, just 3/2 O2 going to O3, okay? Right, and so if I want to calculate the free energy change of that reaction given, right, Gibbs free energy change of that reaction given delta H and delta S, right, I just use the fact that delta G is equal to delta H minus T delta S and just plug in the temperatures, right, 298 and 200 Kelvin, right? So 298 Kelvin, I take the change for that reaction that was given, the entropy change of that reaction which was given, convert it to kilojoules here to get a positive 4.2 kilojoules at 298 Kelvin. If I do the same process at 200 Kelvin, okay, I get a negative 5.9 kilojoules, okay, which is telling me that right, it is not spontaneous at 298 Kelvin, but it is spontaneous at 200 Kelvin. Okay? So it's a question so far about kind of what's done here, right? Again, the problem I'm looking at, is the reaction spontaneous at 298 Kelvin? Is it spontaneous at 200 Kelvin, right? Dealing with the chemical reaction, going to be under temperature pressure conditions, okay? And so under those constant temperature pressure conditions, right, I can use Gibbs free energy to tell me about spontaneity. And so I just need to calculate delta G, which is delta H minus T delta S. And we're given delta H and delta S in the problem, okay? In the second part, I am assuming that the enthalpy is not constant with that change in temperature, okay? So in order to calculate the Gibbs free energy change at 200 Kelvin, I need to know what the enthalpy change is at 200 Kelvin. And to use that, I need to use Kirchhoff's or whatever law, right? Delta H, right? The change in enthalpy with respect to change in temperature is equal to the change in heat capacities times the change in temperature, okay? So the change in heat capacities is the heat capacity of O3 minus 3/2 times the heat capacity of O2, right? I have to multiply by the stoichiometric coefficient. Gives me a delta CP of minus 10.05 joules per Kelvin mole. Okay, plugging that in to the equation above, converting kilojoules to joules, you get the new enthalpy is just minus 24.5 kilojoules. So not much of a change in enthalpy. Okay. I'm plugging that in now, the new enthalpy at 200 Kelvin into the delta G equation. Okay. Gives you a delta G of negative 5 kilojoules. So it's still negative, right? So it's still spontaneous. It just went from negative 5.9 to negative 5. Okay. But this is still going to be spontaneous. I know I kind of rushed through that a little bit, but you know, if you have questions about it, feel free to ask about why we did what we did in this problem. So that definitely covers like what is required for the homework that's due on Friday. So we'll leave the homework that's been due on Friday. I'm pulling up the homework now just to verify here. Yeah. Yeah. So if you haven't started the homework, I very much suggest you do so, because you know a lot of these problems you potentially have to calculate multiple things, kind of like in homework number 2. That so you know some of these questions can take some time if you haven't started. But
Go to the next slide real quick.
yeah.
So why is the delta G on top of the mole?
Huh? Oh, because I was lazy and forgot to write the per mole here.
Is it per mole?
Yeah. Yeah, this per mole, because all the enthalpies and entropy are given in per mole quantities, and nowhere in this, like, and in the problem, it's just asking whether or not it's spontaneous, right? And multiplying by a number of moles, won't change whether or not it's positive or negative, right? And so yeah, in this problem, everything's done in kind of the molar quantity, so everything's per mole here. So I accidentally dropped off that per mole. It's the same thing here. This should be kilojoules per mole. That should be kilojoules per mole. And this delta T, okay, I did put per mole here, right? So I made a mistake on here with kind of just dropping some of my per moles, but it should be, everything should be per mole. Yeah. So typically, Gibbs free energies of reactions and things like that are per mole quantities, even if they don't explicitly say like the molar Gibbs free energy of the reaction. And I promise it's not just me that does that. It's just common that when you talk about free energy changes of reactions and enthalpy changes of reactions and things like that, it's assumed that they're molar quantities. And then often you'll talk about what is the total free energy change when so many moles have been, things like that. And, try to imply when you're not dealing with the per mole quantity. Other questions? All right, so that will be it for today. We'll kind of go over more of some of the things that are on these slides next time, talking more about Gibbs free energy, Helmholtz free energy, and internal energy on Friday. Anyone on Zoom have any questions before I close out the session here? All right, see you guys on Friday.